Good afternoon. Today we have our last theoretical lecture, at least because the exercises still we have a couple, maybe 2 exercises more. But for the lecture, we have today our last lecture about hidden Markov models. Actually, my plan was to cover also reinforcement learning, but unfortunately, the time ran fast, and so we will have today our last lecture in this course about hidden Markov models. And we will see today what is Markov models and what is hidden Markov models, what is the difference between hidden Markov and observable Markov, and then how it could be used in machine learning, and also how to construct some practical application with hidden Markov models in machine learning. Okay, what we have seen so far in machine learning, we are assuming that the instances, they are independent. So every time that we consider that the instances always, they are independent, and we were able to build some machine learning algorithms with this assumption, which could work in many applications, but also it is not accurate for other applications as well, especially that when we have dynamic system, so it is not that valid assumption. Usually we have this simple example of handwriting recognition. So if we would like to have, like, for example, some word that we would like to recognize. For example, if I wrote my name, for example. So this is handwriting, and then we want to recognize this word automatically. So usually, as we have seen before, that we are looking for the probability, for example, of the word. If we call the word like letter I is the I letter in this word. So letter I, based on the attributes, as we have seen many times, like in classification, for example, in part 4 in this course. So we were looking for the probability of, what is the probability of Li based on some attributes. The attributes here can be, for example, the pixels. For example, if we take every pixel, or every letter, for example, A, we can divide it into like matrix in this way, and then we find the pixels in each block here. So maybe we have like 6 by 6, for example, or 7 by 7. So we have, if it is 7 by 7, then we would have 49 like row with 49 pixels. Those represents xi. Okay. And then we are looking at what is the probability of being letter A based on the attributes of the letter, and then we select just the maximum. We are looking for the maximum, and we saw already that from Bayesian theorem that this could be written like probability of Li given the attributes xi equal to the probability of xi given Li times the probability of Li divided by the probability of xi, okay, the event probability. Okay, so now maximum likelihood is by maximizing this one. The probability of Li depends on the language. If every language, it has certain probability for each letter. And now for this likelihood, we are looking for the maximizing of this likelihood, and we can compute it, this one, based on learning, for example. So based on learning, for example, for certain person, then we can build this probability. Then we can find, for example, the maximum a posteriori of the letter. You can see here that we didn't talk at all about what is the correlation between letters here. Okay, but the probability of error here can be high, can be large sometimes, especially for some people that they don't differentiate between, for example, U and V. It is very difficult. Here also, it is hard to say that they are double M. because they are connected to each other. So it can be like n, for example. It is the same, like n, or double m. So how the handwriting recognition, how it could work in this case. So it is better to have the correlation into account. For example, instead of looking for this probability, so we can say that we are looking for the probability of being li, for example, equal to certain letter, given the attributes, but also given li minus 1. So we are looking also for the previous letter. We are looking also for the previous letter, or also for the 2 previous letters, for example. In that case, we can improve the quality and the accuracy of the recognition. Because we know that when you have a Q, then like the next letter, if even someone wrote it like this one, like V, but we know that most likely it is a mistake here, and it should be U, because we know that in English language, at least, we have the probability of being U after Q is much larger than the probability of being V after Q. But if we separate each letter alone and we start just to talk about each letter separately, in that case, the machine learning will not be able to recognize this fact. So in that case, we take into account also the previous case. So we have correlation between events now, or we have correlation and dependency between instances, not only in the handwriting, but also in the voice recognition, for example, or speech recognition. And in the stock market also, as we will see later. So in that case, we need some different methodology to deal with this dependency between instances or between events. So in Markov chain, in general, or Markov model, before we talk about hidden, but in Markov model, usually we say that the probability of being at certain state, for example, the state, we call it like Qt. Qt is the states at time t, or not necessarily time, by the way. It can be also the position here, the position in letter. It can be space. It can be location of the DNA, for example. It can be anything. But here we just, because like some independent parameter like time, Qt to be at state Si. Here we assume that the problem that we have like finite or discrete states, like letters here. So in letters here we can call that every letter as a different state. So the probability of being at time t at state Si, given that at Qt minus 1 it was at state, for example, Sj, and Q at time t minus 2 it was at state Sk, and so on, until Q0, until the starting of this observation to be at state, let's say, S anything, maybe M, okay? Markov, like first order Markov, it says that this probability, even if they are all correlated, but this could be specified as probability of to be at state Si, given a Qt minus 1 to be at state Sj. So it means that wherever you are in the future, for example, this is our current time t, okay? So the future, the state in the future, at t plus 1, this is discrete Markov. Of course, we have also continuous Markov, but we will talk about here only about discrete one. So the state at t plus 1 depends only on the state at t. So the future depends only on the current state. It doesn't depend how we reach to state t. So we might reach from this direction. We might reach from that direction in this way. It might reach from that direction. It doesn't matter. So the future at t plus 1 depends on our state at time t. So this is called Markov, or at least first order Markov process. So this is very important in many applications and to describe dynamic systems. So this is very important. And we will see today some mathematical foundations of Markov models in general. In fast way, of course, we are not going to explain those things in very details because it is long subject, but at least we will try to touch the most important parts of Markov and Hidden Markov process. Okay. In the first few slides, I just gave some possible applications for Markovian, like correlated dynamics, for example, in temporal pattern recognition, like speech recognition, handwriting, pattern theory, and also to describe stock market and many other things. The idea here that we assume we have like n distinct states, like for example in the letters, in handwriting letters, then we have, for example, 24 letters, for example, then every letter is a distinct state in that case. Or the market, for example, we can talk about the market as we will see later, or about some certain diseases or whatever. Okay, and Qt equals Si means that the states at time t or at instance t is at state Si. Okay, and this is what I was talking about. This is the probability. So in the Markov model, in the first order Markov model, that the probability of being at state Sj at time t plus 1, given that at time t you were at state Si, or currently you are at state Si, the future of being at state Sj depends only on this current state. It doesn't depend on the past. Okay. We call this transition probability from state I to state j as Aij. Okay, and actually today we are talking mainly about homogeneous Markovian. Means that it doesn't depend on the time. So in general, A should depend also on the time, but this has some smaller applications in physics and so on. But today we will mainly talk about the homogeneous Markov, which is not, it doesn't depend on the time or on the location. So in that case, Aij is the same as A at time t Aij. So it doesn't depend on the instance where we are looking. So it depends only on the transition from state I to state j. It is homogeneous at each time. Of course, when you take the summation over every row, it should be 1, because from state you have to go to some other state at each time of transition. So this is example for the 3 states problem. So you can see here, now we are not talking about hidden yet. So now just we talk about Markovian-like process. So in the Markovian process, you can see that we have 3 states, state 1, state 2, and state 3. So the probability that you start with state 1, we call it by 1, and the probability that you start from state 2, we call it by 2, and state 3 is by 3. So because you have to start from one of those states, then the summation of Bi over all states must be 1. Because usually when the process starts, we had to start from one of those states. And what this figure means, it is a transition graph. So here the probability that you was in state 1 and next state you move to state 1 again, then it is given as A11. You was in state 1, the probability that you move from state 1 to state 2 is given by A12. And from state 2 to state 1, A21. From state 2 to state 2 is A22, and so on. So it is very easy to be represented. Okay? What this means, it can represent anything. For example, for those who came from finance or economy, this can be stock market. State 1 can be bull market. State 2 can be bear market. And state 3 can be stagnant market. So now you study the market. So the market can be, for example, if you take the observation every day. So what is the probability that today the market is bull market going up, and tomorrow it will be also going up? Then it is A11. What is the probability that the market is bull market, but tomorrow it will be bear market? Then the probability is A12, and so on. So this can represent the market changes, for example. Okay. This is a simple example that we generate only one signal, like -1 and +1, and we put it in two different ways. First, that if it is IID, it means identical and independent distribution. So it is -1 +1, it is equally likely, it means 0.5, 0.5. And here if we assume that they are like correlated, if you start with -1, the probability of being -1 again is only 0.1, but to move from -1 to 1 will be 0.9. And if you are at 1, the probability that you go to -1 is 0.3. And if you are at 1, the probability of stay at 1 is 0.7. So this can be done very easily on Octave or any programming language. And then we got, it is not that clear on the slide, but it shows that how it will be. In the case of independent, identical distribution, so you will have the mean equal to 0 and the variance equal to 1, and it will be like equally likely. But here you can see that most of the time it is at 1, more than -1 according to the correlation properties. And in that case, the mean is not 0, but it is 0.52, and the variance is 0.73. Okay. Now, in the observable Markov process, we start with the observable, then we go to the hidden. In the observable Markov process, that the observation is already the state of the market. So, for example, if we go back to the market case, so we know exactly, based on some symptoms that we are looking, that if this symptom happen, then we are in like bull market. For example, if symptom 2 happen, then we are in bear market, and based on the observation, if that symptom happen, then we are in a stagnant market. So we know exactly that every time we see the states of the Markov. So this is called observable. So the states are observable directly. Okay, and then we have this observation, and now what is the probability that you will have certain observation based on the matrix A. Matrix A is the if we take the same example of the stock market, so we have here the bull market, and we have here the bear market, and then we have the stagnant market. So we have this probability. So here to be 1 and go to 1, from 1 to 2, and then from 2 to 1, and from 1 to 3, and from 3 to 1, from 2 to 3, and from 3 to 2, and here from 2 to 2, and from 3 to 3. So these are all the possible transitions. Then what we have here, we will have matrix A. Matrix A gives 1, A11, A12, A13, A21, A22, A23, and A31, A32, A33. The summation of each row must be 1, because if you are in stage 1, next time you have to move somewhere, either to same stage, A11, or to go from 1 to 2, then it is A12, or from 1 to 3, then A13. So the summation of each row must be 1. And also we start with certain probability. So we can start with 1 with by 1, and start with 2 with by 2, and start with 3 with by 3. Okay. Now, if you have been given that you study about like history or something about the market, how it was, and you found that the market started to be like stagnant at certain time. So it was 3, then it goes to 3 next time, then it goes to 2, then it goes to 1. And what is the probability this transition will happen? What is the probability that this transition will happen? How to calculate it? This is Q1, this is Q2, and this is Q3, and this is Q4. So we have 4 observations. Remember, now the observation represents directly the state of the problem. Okay, what is the probability that we start with stage 3? It is this one, pi 3. Pi 3 is the first probability, that it means that the first observation started with stage 3. Times, then from stage 3, the second observation, it was also in stage 3. Then it is the probability of being in stage 3 and you transit to stage 3. This is given as A3, because from 3 go to 3, times the probability of going from 3 to 2. So it is times A3, 2. And then from 2 going to 1, then times A3, 1. It is as simple like that. So if you have this matrix A, you can very easily calculate the probability of each transition in that Markov process. This is actually the power of Markovian analysis, that it makes problems, correlated problems, very, very simple. So you can easily calculate it in this way. Because you have, now we assume that you have the matrix A. I will show you later how to calculate it in the learning process. But now we have the matrix A, or at least the estimation of matrix A, and we have also estimations of by 1, by 2, and by 3, then we can calculate any probability. We can calculate what is the probability, like after 1 year, the market will be like in that state. Okay. So this is the general formulation of the probability. Okay. Now I will have a simple example that we assume that we have three urns. Okay, 3 urns, and each urn, it has balls with the same color, So the urn 1, it has only red balls. Urn 2, it has only blue balls, and urn 3, it has only green balls. And every time there is someone show the ball, that he just take the one ball out from the urn, and then we know that it means that we have 3 states here. State 1 is red, state 2 is blue, and state 3 is green. And the states are observable. Why? Because each urn has only one colored ball. If there is multiple balls, then it can be hidden, as we will see later. But now every urn has only one color. Okay. And also they give us that the initial probability of each urn to start with is 0.5 for the urn 1, which contains red balls, 0.2 for the urn 2, which contains blue balls, and 0.3 for the urn 3, which contains green balls. And also it was given the probability matrix A as this matrix, and now we can see in this figure how to represent this problem. So if you selected the first urn, which contains red balls, then the probability that you will select again the same urn is 0.4. And the probability that you move to the second state is 0.3. The probability that you go to the third state is also 0.3. From where we got this? From this given matrix. And so on. So of course, all the others can be easily extracted from the matrix A. Okay? Now, if you want to compute, if I asked you what is the probability that the observation will be S1, S1, S3, S3, it means that red, red, blue, blue, or green, green. Yes, it is. The third one is green, so it will be like red, red, green, green. What is the probability of obtaining this observation? The probability is easy like that. B of S1, the probability that we start with the first urn, it is given. It is 0.5. It is 0.5. Okay, and then this one will be 0.5 times the probability, because the second one was also red. It means that we selected the second, the same urn again, the same states. Then in that case, it is A11. A11, it is given also like 0.4. Okay, and then A13, because here we transit from red to the green. So from S1 to S3 is A13. A13 is given like A13 is 0.3. Okay, and so on. So we can calculate the probability for each case. Okay. Now, the situation, if we look from the reverse direction, is that we have observations and we are interested to build the matrix A. This is the learning part, if we can call it learning. So now we are estimating those parameters A and Y matrix and A matrix are from observations. Okay. Now we have observations. I put it here. 1, it means that the first observation. So we see here, for example, how the balls were changing the colors. So, for example, red, green, blue, red, and so on. And then we have, this is the second observation. Every observation contains T different transitions. And remember here, what we see here is the states. It is observable Markov, not hidden Markov yet. And we have seen like K different observations. From those K different observations, we can build or we can estimate the likelihood estimation of the matrix A and also for the bi matrix. It is simply like that. What is the probability that we start with the first state 1? What we check? We check only the first time. Okay. Now, let us that we have K here. We have 100 observation. So we have like red, blue, green, and so on. And then the second time we have like a green, red, blue, and so on. And until we have like red, and so on. So we have 100 observation. 100 observation. How to calculate the probability that we started with red? Simply, we count how many red we have. Okay, and divide by the total number. Hey, K equal 200. Then, for example, if we found that red like repeated 30 times, simply the probability that S1 equal to red is equal to 30 divided by 100. It is like simple like that. So we just count how many numbers that we have, then we can calculate the probability. Okay, how could we compute the probability of transition from 1 to 2, for example? Okay, we come for each observation and we check where we have states 1 and states 2. 1 and 2, for example, of course, those are Q, so they are not representing directly the states. But, for example, assume that we are looking to calculate the probability A, 1, 2, which means that we move from red to blue. Okay? So, now we start. Here we have from red to blue. It is 1. Okay? And we are looking. We found another one from red to blue. This will be 2. Okay? And we found in the second part from red to blue, this is 3. So we count every instance where we have from red to blue. And then we divide over all cases where we have red. Because we are looking from red to blue. For example, here we have red. But it was not from red to blue. It was from red to red. So this is 1. We count every time where we have red, okay, in all observations, and then we count how many times we have the transition from red to blue, and we divide them together as it is shown here. So transition from Si to Sj divided by the number of all transitions from Si. Wherever we have Si, for example, the red ball, then we take into account. And we take the summation over all instances in time and also over all observations. Here, 1 of, it means that it is indicator function. 1 of x means that 1 if x is true and 0 if x is false. So this is just indicator function to count the number of events. Okay, this is just exercise that to calculate or to build the observations using Octave, the data given already in the model. Okay. And as I said, this is just a repetition where I started this lecture with when I was talking about the probability of the letters and where is the rule of Markov here. Where is the rule of Markov here to work? Okay. Yes. Yeah. Now we come to the hidden Markov. We come now to the main topic actually of this lecture, but because
Many of you maybe they didn't know about Markov in general, what it means. So we started with the general Markov, but now we come to the hidden Markov. Okay, what is hidden Markov and why it is very important, and what is its rules in machine learning? Actually, hidden Markov is means simply that the situation where the states are not clear. For example, if we take the states of the handwritten or handwriting recognition. So we have the states here, like for example, letter A and letter B and letter, for example, until Z. And we have capital and small and comma and everything, okay? Yeah. Now we have observation. We have observation is based on the handwriting like letters. So we have here in the observation. The observation here is not necessarily being to know directly in which letter we were. For example, if someone writing A very similar, the way that he wrote A very similar to, let's say, to U, very similar to V, very similar to Y. So when he writes, he doesn't recognize very well between those letters. Okay, so it is very difficult to recognize what he wrote. In that case, when we see the observation will not tell us directly in which state we are. So we have this observation it can be A, it can be, for example, somewhere here we have U, and somewhere we have V, and we have Y. It can be A, it can be U, it can be V, it can be Y. So the letter that we saw now, when we make this like scanning for the letter, for example, it was something like this. We don't know what he means here. Is it A? It can be with certain probability to be A, with certain probability can be U, with certain probability can be V, with certain probability can be Y, because he doesn't recognize between these letters. Of course, here because of the language, we know that the probability from A, like A11, we have loss transition. We have loss transition, of course, as we saw before, but the states are not observable. What we can see, we see some observation. The observation is related to the states with certain uncertainty. With certain uncertainty, it looks interesting. Certain uncertainties. Okay, so there is some probability with each state. Now we have two kinds of uncertainties here. We have the matrix A, which control the states transition with certain uncertainty, and also we have another matrix B, which represents the probability or the connection between the observation and each state. In the beginning, maybe it looks like confusing a little bit, but I will explain them in very details and also with some numerical example to understand it very well. Okay, so here we have some observations from V1 until Vm. So what I define here, we define a new parameter like B at time t, and this means that this is the probability that observation M came from state J. So now we have the probability, but you can see that I put here the observation time or instance T, but then I removed it. So it is like homogeneous. It doesn't depend on the time. So in that case, we define BJM as the probability that O means the observation. The observation at time T, it was certain observation Vm, given that it came from states Sj. This is the probability BJM. Okay. Of course, we will see some applications about this. Okay. But before that, now the states are hidden. We don't see the states. We see observation. We see the observation, but we cannot. Or the states are hidden. Okay, but it can be inferred. It can be inferred based on the observation. Okay, this is the problem now. So it is a little bit different than before. Before what we had only the states. But now we have the states, the transition between states, but there is a hidden part. We cannot see, we cannot look to the states. What we can see, we see the observation part is V1, the observation, for example, certain observation, and V1, there is a probability of being from state 1. Like we call it B11. B11 means that it came from state 1 to observation 1. Here, B21 is the probability that V1 observed, the observed V1 came from state S2. B31 is the probability that the observed V1 came from state S3. And here, for example, the probability that you observed V2, the probability that it came from S4 is B42. So it is now we have these probabilities that controls the connection between the observation and the actual states that they are hidden now. We don't know them. Just before I go with the explanation of this, I give you a simple example. Now, if you use, like in Siri, in iPhone, for example, at least, I don't know the technology that they are using right now, but at least previous versions, and I'm almost sure that they also use for the current version, that they use hidden Markov models for recognize the voice. When you ask Siri about something, okay? So in that case, what we like to do, we like to know that the states of the phonemes. That when I talk, for example, I say, what is the temperature tomorrow? Okay, what is this WHAT? So you can see when you talk to iPhone, you can see that what you are saying is written. So how they can recognize the voice? Usually, of course, they use like mini learning data they have already, but also if you want to increase the accuracy of your iPhone, they ask you to make some training. In the training, they know the series. They give you certain like words, and they ask you to read them. Okay? When they give you certain words, they actually know how it will be the states because they gave you the words already. And the way that you saying them, you give to the iPhone the observation. So you give them the observation, and they know the states what Siri will build, in this case, what the algorithm will build. The algorithm will build this observation probability. This P, it will build the probability P and also the matrix A. Of course, the matrix A some of the matrix depends on the way that, on the language itself actually, and also part of it depends on the people, how they saying words. We will see later more about this voice recognition example. But before that, I just about this states of the stock market. The example of the stock market for those who came from finance. So you can see that the market can be like in bull states and in stagnant or in bear states. Okay, but actually we don't have direct. We are not 100% sure that at what states the market is now. But we have some symptoms measure. For example, the share prices for certain companies, for example, or some political situations, for example. So the oil price. So we have some symptoms, and based on those symptoms, we have some observations. But those symptoms are connected actually to the actual states of the market. But the actual states of the market, we don't know it exactly how it will be, but we have certain probabilities between the symptoms and every states of the market. So this is one example of the hidden Markov and why it is extremely important in dynamic systems like in stock market analysis or whatever. I will take this simple example and try to explain together the concept of hidden Markov with quite simple example. In this example, we have only two errors. Okay, one error. So the states are the errors. So we have like error 1 and error 2. Error 1 contains like 8 balls, 4 red 1 white, and 5 black. Yes, it is 3, 4, and 1. Sorry, it is 3 red, 4 white, and 1 black. So the total are 8. For the L2 contains 4 red, 1 white, and 5 black. So the total is 10 balls. So there is a person. Select one of the urns randomly. The urns they have the same color, so we don't know which urn contains which balls. And they just select one ball. If it was red, regardless of the urn, if it was red, he repeated again the process. So he rebut the ball inside and then draw another ball. If it was red, then he repeat. So he like continue in the same urn as far as the drawn ball was red. If it is different color, then he will switch to the other urn. But for us as observation, we see only the colors of the balls. We don't see the states themselves. So this is one simple example about hidden Markov. So we can see here, this is the example. We have urn 1, we have urn 2, and the observation that we have either white ball or red ball or black ball. But we don't know from where each one comes. Okay, so now based on these balls, we are interested to know what was the states every time, what was the state sequence. For example, if from this example, if we have like white, white, red, white, black, white, red, white, and now this is observation. We are interested to know how was the transition in the states, like U1, U1, U2, U1, U2. Why? If we know this transition, then we solve the problem, because this can be given to the machine learning to know how was the states like the transition, how it was. Okay. Now, so let us solve this problem first. What is the probability of selecting urn 1 or urn 2? Of course, this is state 1 and state 2 because they are blindly selected, so it will be equally likely, and selecting each one from the beginning is 0.5. Okay, now let us calculate A11. If you select the first state, which is urn 1, what is the probability that you will go next state to the same urn? Let us see. Urn 1 contains 3 red, 4 white, 1 black. The total is 8. The probability that you will select another, you will select red ball, it will be 3 divided by 8. 3 because you have 3 red, and then the total is 8. So the probability that you will go, because this was the example. The example was you will repeat the same state if you got a red ball. So the probability that you will get red ball is 3 divided by 8 because we have 3 red balls and the total number of balls is 8. Then the probability that you move from urn 1 to urn 2, A12, it means that you selected different ball. Different ball means that the rest is 5, so it is 5 divided by 8. Okay, and now if you are at state 2, it means that at urn 2, what is the probability that you will go to state 1? So it is A21. A21 means that you selected a ball which is not red. In state 2, how many red ball we have? We have 4, and the total is 10. So the rest means that there are 6 balls. So it will be 6 divided by 10, and the probability that you will stay in the same state 2 is that selecting the red ball again, which is 4 over 10, because the rest is 4 balls, or 2 over 5. So this is actually the matrix A. So simply we can build matrix A in this way. Okay, now we build matrix B. Matrix B, B11. What means B11? Means that what is the probability that you will get white if you are at state 1. If you are at state 1, what is the probability that you will get the white ball? Let us check. In state 1, how many white balls? We have 4. The total of balls are 8. So simply it is 4 divided by 8. Okay? Simply it will be 4 divided by 8. Okay. What is the probability that you will get the red color given that you was in state 1? It is simply like that. Actually, we calculated this because we have 3 red balls and we have the total is 8, so the probability is 3 divided by 8. B13 is the probability because 3 means the color black. So the probability that you will get black color or black ball given that you are at stage 1, earn 1. We have only 1 ball, black at earn 1, so it is 1 over 8. And in the same manner, we can calculate all this B probability. So now we have A, we have B, and we have Y. Y is the probability that you select each area. Now, it is quite trivial to solve such problems. Of course, it is very small and very simple problem. If the problem is much larger, of course, it can be more difficult. But even in this situation, if we think in different way, in the reverse way, that I give you the observation, and I want you to estimate the matrix A, B, and Y. This is actually the machine learning. The machine learning now, we are interested that based on observation, we like to estimate what are the parameters of the hidden Markov. But hopefully that hidden Markov now is clear what it means. So now if you have, for example, one observation like white, white, black, white, red, black, red, red, and so on. And the second observation, we have black, white, red, black, and the third observation, fourth observation. And then I asked you to build or to estimate what are A and B. Or sometimes I give you A and B, but I ask you to calculate what is the transition states that happen. So actually they are not trivial, but we will see how to do it. In the previous example, what is the probability that you will have, the observation that you had is red, red, white, blue, or black, red, red, white, black. And I asked you, what is the probability that the stage sequence was like earn 1, earn 2, earn 2, earn 1, or state 1, state 2, state 2, state 1. What is the probability of that? Okay, what we are looking for, we are looking for the probability that Q1 started with earn 1, Q2, earn 2, Q3 is earn 2 also, and Q4, the states at time 4 is earn 1. This could be calculated simply like that. The probability that Q1 equal to U1 because we started with U1. So this is the state 1. Then from 1 we go to what? To 2. So then the probability that from 1 go to 2, so it is A, 1, 2. Time is the probability that you go from 2 to 2. So it is A to 2. Then time is the probability that you go from 2 to 1. Then A to 1. Okay? Times. The first part was related to what? Like observable. Like the observable Markov. But now it is hidden because the red can be from any of the earners, 1 or 2. But we are looking for this probability. Then this is the probability that, what is the probability that the observation 1 is red, given that the first state is U1. The probability that the second observation is red, given that it came from earn 2. The probability that the third observation is white, given that it came from earn 2 again. And finally, the probability that the fourth observation is black, given from the first earn. Then we can put them in this way. So it is by 1, this probability, A12, A22, A21. Then B1 of R, B1 of R, B2, 1 and 2 here means that states. And the color is the red is 1, the blue is, the red is 2, and the black is 3. So we can calculate them, and from the matrix, from this matrix, you can actually calculate all this probability. Okay, we have take a break now because the topic is we will take only 10 minutes today. Okay, like break 10 minutes. Then I show you how to do it with in Octave. How to only with this one line actually. Or 2 lines you can generate hidden Markov, and I show you also how to build or how to get learning process, or to build a learning process based on observations in hidden Markov models. So we have 10 minutes break and then we continue. Yeah. Hello again. So we continue. We have already given some simple example that we have only two states, L1 and L2, and there are some mixed colors with different percentages for each one, and both of them, they might have like white and red and black, and then we have the observation only the colors come from the urn or from the urn without knowing which one. So it is like hidden Markov, and we just explained how to build the parameters of this hidden Markov represented by the matrix A, matrix P, and by which represents the starting or the initial probabilities of each state. How to generate those? Of course, you can generate them like by writing some code, but we have already built already functions to do that. In Octave or Matlab, they use HMM, means that hidden Markov model, generate. So, for example, in this function, you can see that you put the matrix A, the transition matrix A. I just took it from the example, so 3/8, 5/8, 3/5, and 2/5. So you can see that I put them here. So it is 3/8 and 5/8 and 3/5 and 2/5. This is the transition probability matrix. And then we have matrix P, which represents the observation probability or the output probability. And also it was taken from the calculations. And then you can put some symbols for your output and your state names in this function. So the output that we have white, red, and blue, and black, the colors, you can write them, of course. You can write white, or you can do put any symbols here. And also the state names, you can call them like 1 and 2, or actually by default it will be 1 and 2. But if you like to see like Earn1 and Earn2, you like to see like S1 and S2, you can write whatever you like to see in the output. Then T is the number of generated outputs, so I put it 30. I forgot to put T here, it should be T, so you can change it easily, but anyhow. So it is HMM generate. The first element you put is the number of generated sequence. 30 means that it is 30 outputs. Then you put matrix A, matrix P, and then you put the symbols. The symbols means that it is the output symbols. It is the outputs, which means that white, red, and blue. And then the state names. The states names that it is given here like state names that U1 and U2. And once you run this code, you will get the result that this result we obtained. It gave us like red, white, red, white, red, 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 white, black, red, and so on. And this was the state transition. The state transition, it was U1, 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 U2, U1, and so on. And second run, I made the run again for the same code. Of course, it will give different result. So it gives another sequence with different also state transition, because the state transition is based on probability. So how it works actually? One way, for example, how the code works. For example, if you have for example, that state S1 and state S2, state S1 and state S2, okay, and then the probability to go from state S1 to state S2, for example, it was 0.6, for example, and then from state 1 to state 1 is 0.4. Okay, then one way to do it, so you can generate a random number from 0 to 1. Okay, and the obtained number that you get, it is just random number that you generate, like rand 1. you generate a random number, like uniform from 0 to 1. If the result was from 0 to 0.6, then you take the transition. If the result was from more than 0.6 up to 1, then you take the same state. Just like that. So every time you repeat the problem, you might get different result. Okay, it depends because there's uncertainty. There's a chance to move or not to move. Okay, so this is the way that how it works. So every time you repeat the same example, you might get, or always actually you will get different results. Okay. Remember, even they are different results, but if we think in different way, so if we have this result, A and B will be always the maximum likelihood matrices of the problem, that which generates this one. Okay, let me explain this. If I give you just sequence of number 1, 2, 3, and 4. Okay, this number can be generated. For example, if I told you that these numbers was generated by normal distribution n with mean mu and variance sigma square. Okay, actually any normal distribution can generate these numbers. Okay, any normal with any mu with any sigma square, they can generate 1, 2, 3. Which one we should select from those? We should select those which have the maximum likelihood or the highest chance that will generate those numbers. How to calculate them? As we saw from the part 2 or part 3, that we compute, for example, the maximum likelihood estimation of the mean will be 1 plus 2 plus 3 plus 4 divided by 4. This is the mean. And then the variance, we can calculate also like the summation of this mean minus this one. So it is summation of those inputs I minus the mean square from I equal to 1 up to 4 divided by n minus 1 divided by 3. This will give you the unbiased estimation for the variance. So the normal distribution with this mean and this variance will be the maximum likelihood or the best distribution to generate these numbers. But in general, any u, mu, and sigma square might generate those numbers. It is the same here. Actually, any sequence u1 and u2, any matrix A, any matrix B, as far as we don't have zeros that to make them zero, no one will be generated, but we have infinity number of A and B can generate the same sequence. But which one we select? We select the one which give the maximum likelihood estimate based on the observation. Okay. Now we like to see how this will work and how could we estimate the best sequence to generate this observation. So now we have only two stages. This is the figure here is given for in general, but if we restrict ourselves with our example that we have two states here, like Ln1 and Ln2 only. Okay. So we have like Ln1 and we have Ln2, and at certain time, so this is the time, observation 1. At time 2, we have another 1 and 2. At time 3, it is like this. Time 2, time 3, and so on. Okay? For each one, what is the probability that we start with Ln1 is by 1. And probability that we start with Ln2 is by 2. It was given in the example like 0.5 and 0.5. Okay. Or from Ln1, we can go to Ln1 or we can go to Ln2. From Ln2, we can go to Ln1 and we can go to Ln2. This from 1 to 1 is A11, from 2 to 2 is A22, from 2 to 1 is A21, from 1 to 2 is A12. It is simply like that. And it continues. So it is like A11, A12, A21, and A22, and we continue in this way. Okay? Now, based on the first observation, so we can take one example. For example, if we have this red, white, blue. So red, there is a chance that we get red from this state, or we get red from this state. It is possible. So the observation can be from state 1 or from state 2. And the second is red. It can be also from state 1 or from state 2. The third is white. It can be from state 1 or from state 2. Now, assume that we have, just pay attention for this. Assume now you know matrix A, you know matrix A, you know matrix B. So you have A, you have B, okay, and you have the observation O. So you know what was the observation, like red, red, white, black, red. You have the observation and you have the matrices. We are interested now to know the states, how it was. So it is like here, like U1, U2, U1, U1, and so on. So we are interested to know how the states were changing to recover the problem. I like in the beginning to connect you to the curl of the problem. Why we are doing that? Usually, the problem can be divided into two parts. The first part is the learning. The learning that we give the states, like I said in the Siri example, that when you talk, and then we know the states, and we have the observation, we have states, we have observation, then we can estimate A and B. We estimate A and B. This is the learning phase. Now, in the testing phase, or in the working phase, after we build A and B, we have only the observation, the person who is talking. But we are interested about what? We are interested about the states, how they are. Because the states are the letters, the states are the words, the states are the market. So we are interested to look to the hidden part, is the transition of those states. Okay? So now we have A and B. We build them based on the learning phase, and then we have certain observation. From the observation, we like to estimate the states. Okay, how to estimate them? We have different techniques. One of the most important techniques that it is widely used. Of course, we can in this simple example, we can calculate the best one. But if the problem is large, it can be almost impossible to calculate the best one based on the finding the optimal solution. It is almost impossible, as we will see later. But it can be done based on the Btob decoder. This is called Btob decoder, and the idea here is very simple. The idea here is you start by this one. For example, you calculate the probability by 1. You know the probability by 1. Then you compute the probability that you will have red. Then you, if you move to state 1, if the second red from this state, then you multiply it by A11. Then if it is red from here, you multiply it by the observation red, until you reach to the last one, because you work according to this observation. And then you select the second path. What you select, once you select to the last state, you select the path which has the highest probability. You select the path which has the highest probability. For example, this one, it was from state I to state 1 to state N, and until we reach to the last state. And this state should be the highest like multiplicative probability. However, remember that because we multiply probabilities, and probabilities between 0 and 1, like 0.1 times 0.05 times 0.001 times 0.1, and when this has like many times, like hundreds of times, then the multiplication can be very close or go to close to be 0. And because of that, we need to make some normalization during this process to avoid that become very close to 0, where maybe the computer will not be able, that we will have overflow in the other direction, underflow. And in that context, we can calculate by using Btob decoder, which is efficient way, in order to find the optimum states, how the states were changing, in order to have this based on the optimum or the highest probability solution. Okay. Now, what are the parameters of hidden Markov models? We have 5 important parameters: the number of states, the number of observations, the transition probability A, the observation probability B, and the initial state probabilities pi. Okay. Actually, N and M are already included in the A and B, because A is N by N and B is M by N, or N by M. So we know we can have the number of states and the number of observations from the matrix A and B. Because of that, we call lambda as the parameters of the hidden Markov model as A, the transition probabilities, the observation probabilities, and the initial probabilities, states probabilities pi. If you have given lambda, which contains all parameters, then you can generate the output as we saw before, like using Octave or using Matlab or Python or whatever language that you use. You will find them ready functions there. Okay. However, we are interested in the other direction. We like to estimate the parameters based on the observations. Okay, this is what we are interested here. This is the example of hidden Markov models for speech recognition. If someone is talking, and then we have these phonemes here, that small like letters, how they are spoken, and then we have analog to digital converter to convert these to digital, and then we have acoustic observations like O1, O2 until O3, so they are the observations. Then based on the observations, we have the hidden Markov models. Then we can have the Bayesian, where it gives the name or what the person is saying. For example, hey Siri, what is the temperature tomorrow in Vaasa, for example. And here we are interested to maximize, to find the word which maximize the observation. So now, what is the optimum words which, based on the observation that we have, that it is maximized? This is how it works. Okay, so this by Bayesian theorem, this can be the probability of the observation based on the words, which can be built over learning, and then multiplied by the probability of words, which depends on the language, and probability of the in general probability of the observation, regardless of the words itself. So actually, a hidden Markov model will build this part. Which can be used by the voice recognition, or it can be used by neural networks, for example, or whatever techniques that we use in order to improve the recognition capabilities. We have 3 different problems in hidden Markov models. The first, that you have the model parameter, and you like to evaluate what is the probability of certain sequence, of certain observation. So we are looking for the probability of having certain observation based on the model. This is the first problem that we have. The second problem that we have, that you have the model and the observation, okay, and we like to find the state sequence, Q1, Q2, for example, U1, U2, U3. This was already given by using Btob Decoder, as I said. Btob Decoder, which looking for the path which achieve the highest probability to achieve this output based on the given A and B. So this was already explained. Okay, so now we have the Q is Q1. Q1 means that the state at time 1, it can be state 1, state 2, state 3, depends on the number of states. And the Q2 is the state 2 at time 2, and so on. So now we are looking in the second problem, that to find the optimum states which maximize the probability of the states given the observation and the model. So we have the model, we have the observation, but we are looking to the states. It is like retrieving the problem or solving the problem. The third one is the learning part. The learning part, that you have a training sequence, and based on the training sequence, so you know the states and you have the output. And what you like to build is A and B, and by, of course, and by. So you are looking to build the transition matrix, the observation matrix, and the initial states vector. So this is what you like to build, which is represented by lambda star, which contains that A, B, and by. This is what you are looking to build or to estimate. This is called the training version of the problem. So you have the sequence, you have the states, transition, you have the output, then you build the parameters, or you estimate actually the parameters of the hidden Markov model. So this is the three interesting problems. Actually, in next slides, I explain mathematically in details how to find every one of those. But because of the time, we still have a few minutes, so I might skip some of the mathematical derivations, and I will go to the most important parts in these slides, and mainly how to do it like over Octave. By the way, Octave is given just as an example, so you can apply them in Python or in Julia or whatever language that you use. You can apply them, because in every language there are some ready functions to do that. Yeah. So this is actually, I explained before how to calculate the probability of the observation given states and given certain lambda. Lambda is the parameters. So if this is given for certain q, and if you like, if you know q, then also you can extend them. And we have already given example about this in the previous slides. That in case of two problems, like 2 urn and 3 colors, we can easily build them. So as I said, that I'm going to skip some of those, but in this example, for example, in slide 27, what is the probability that you will have the following observation, like red, white, red, black? So we have 2 urns, and we have three poles. What is the probability that you will have this sequence of red, white, and red, black? So this will be, because we started with red, so what is the probability that you will start with the red color? And given that you are in states Q1, in the beginning we don't know the states yet, so it can be like urn1 or it can be urn2. But this is the first, what we need to compute, the observation probability that you get red, the observation probability that you get white, the observation probability that you get red again, and the observation probability that you get black. This is the first calculation here. So, and now we need to calculate what is the states, because it can be at state 1 and it can be at state 2. In that case, I need to take the summation over all the states that we have. For example, if we have certain lambda, okay, it will be in this way as we saw before. So if we know the states transition that U1 and U2, then you can do it for those states. If you don't know them, then you have to average over all possibilities. Over all possibilities that you take from U1, 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 means that because we have 4 times, or it was U1, 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 U2, U1, U1, U2, U1, and so on. Then we have 2 to the power 4. Then we have 16 possible configuration. So you need to take the summation over 16 possible configuration in order to find that probability. So even in this very simple situation, you can have that much large of chances. So if you have 50, if you have a problem with 50 states, and you have 30 times observation, then the number of possible situation is 50 to the power 30, which means about 10 to the power 51. It is almost impossible to solve such a problem with our current computations for very large problems. And however, as I said, there is very elegant mathematical equations in order to solve those in simple way. One of the methods is called forward-backward procedure, and it makes the problem much easier in order to find the probability of obtaining certain observation based on the parameters. But as I said, that I will skip this because of time. However, for those who are interested, it is explained in details in the slides, so you understand them very well. And this one was the forward, and then we go to the backward, and then we can calculate the probability of certain output given the lambda or the hidden Markov models. And also finding the state sequence, it can be also calculated easily based on these equations, but I will skip them. Okay, now I come to how to calculate or how to do it and this is important, by the way. If you are doing your master thesis, for example, you might not be that much interested how to derive all these equations, because they are available in books already, textbook for many years, but you might be interested more how to solve the problem. And in Octave, I take it as an example, there is a function called hidden Markov model Viterbi. So in that model, or in that function, you just give the output, okay, and also you give the estimation of A and B, then it gives you directly the optimum transition states, how the states were going on. And how it works, I built this simple equation, so you can see this is the whole code. Actually, it is only one function. You can do that. So what I did here, for the same problem of the red and for the two urn with the three colors problem, so we bought matrix A and we have matrix B as before. Then we have the output like white and red and black, and then the state's name like urn 1 and urn 2. Then we have T is the time, okay? So here in the beginning, I generate 20 outputs. As you can see, I generate 20 output. So the output here will be the sequence of the output, like it will give you like red, white, red, and so on. And also it will give you the actual states, because I did them with the HMM generate. Okay. Now we come to the Viterbi. In the Viterbi, we assume that we don't know the actual states. We don't know the actual transition of the states. But what we know only the sequence. So we have the output like white and red and black. So how they are, we have 20 of them as the output, and we have the matrix A and the matrix B, the parameters of the matrix, and also we have here and we like to see the outputs and the states names. So now you can see in this figure that this is the actual states that we have, and this is the estimated based on the Viterbi. Actually, you can see they are identical. They are identical. They are exactly the same. So Viterbi was able to find them perfectly. But why? The reason that we gave the actual A and B, because in real problems we have estimated A and B, not the actual one. But here we gave them the exact A and B, and the size of the problem is small. So in that case, Btob Decoder is able to find the optimum or the right states transition. Of course, it was not always working perfectly. So when I repeated the problem several times with different situation, then I got some errors in the estimated states. And now how to make the learning? The learning that we are looking, what is the optimum parameters? What is the parameters? Is matrix A, matrix B, and Y, which maximize the observation based on lambda. So this is what we are looking for. And this also we have some mathematical derivations how to do it, but again I will skip them and come to it is based on what we know them as expected maximization or expectation maximization problem that we have already solved it in the clustering problem. Anyhow, so I will skip those until we come to the implementation. So in the implementation, you can see that in Octave there is a function. It's called hidden Markov model estimate. In the hidden Markov model estimate, so you need to estimate what is A and B. What you give the states and the observation. You give the states and the observation. It is like the training. When you are training your Markov model, for example, for certain person that he's talking, then you give him some text. Read this text. When he read the text, then you know the states because you know already the text. And the way that he's saying the text, then this is the observation. Based on the observation and the states, you can estimate for this person what is A and B and Y. And in that case, it works like that. So you can see I generated A and I generated B, and then this is the output names again. The state name is U1 and U2, and then we have 30 times of generated output. Then this is HMM generate, so I generate the output. But in the HMM estimate, you can see what is the input. The input is the sequence. The sequence is the observation. This is the observation, like red, red, white, red, red, and so on. And also, you give it the actual states transition. So you give it O and you give U. You give both of them. And you ask them to estimate what is the best transition probability and the best output probability. Okay, now when I did this example, I get this result. So the best transition probability was 0.6667 and 0.33 and 0.5. What is the actual A? Actual A is 0.37, as you can see, and 0.62 and 0.6 and 0.4. Actually, it is clear there is error. There is error between this and this. Of course, it is not very bad, but it is the best estimate that the HMM estimate was able to do. For the output probability, it is okay. You can see that it is 0.27 here. It is 0.5. 0.58 it is 0.37, and 0.12 it is 0.22. Actually, this one perfect. 0.5, 0.41 it is also 0.40. 0.028 it is 1.1. So you can see that for the second state, it is the estimation is much better. And actually you can see also the estimation of the second state is better also in the transition probability. So there is error here, but this is what we have. This is the best estimation based on this result. Okay. So this is the way that we can build our function based on that. I increased in the second one. I increased to 200 sequence of learning, and then we can see there is some improvement in the result. So you can see it becomes like in the best transition probability estimate, it becomes 0.46, here it is 0.37, 0.5, 0.66, and this is 0.60, 0.39, so it becomes much better. And also for that best probability, it becomes even also quite good. So as more sequences that you have, then better learning result you will obtain. Once you build, this is the like A hat, the estimation of A and the estimation of B, then you can use them to in order to estimate by using Btob Decoder, and also to estimate the sequences states. And this can be given for like upper layer, like neural networks, or if you are using, for example, some kind of a classification or clustering, like dynamic clustering or dynamic classification, then you can give these results in order to build the best classification. So hidden Markov models is part of the classification, or is part of bigger machine learning algorithm. Of course, you can consider it as part of machine learning itself, but usually it gives the optimum of probability of y based on x in order for the Bayesian classification to be used. That's all about hidden Markov. So now we know the Markov is to represent some dynamic changes, and if the states are not observable, then they are hidden. Then we need to build some probability in order to reach them, and they are actually different order. What we studied today is only first order. We have continuous Markov. We have multiple levels of multiple orders of Markov. So this is very basic. This is homogeneous. It doesn't depend on time. The problem can be much more complicated, of course, if you consider like non-homogeneous case, or for example, or multiple orders. That's all. And finally, regarding report of the course. The deadline, as you know, that is 15th of April, and I encourage everyone to send that even simple problem. Don't complicate things. I mean, in this report, I'm not looking that you have real data and you apply them. It can be, of course, it can be master thesis. This work can be master thesis if you want to build like complete work. It is not required in this way. What we need just to have some data, that whatever data that you have, and you apply some of those machine learning algorithms that we have seen already in the course. You can contact the instructor of this course in order to help you if you need help in Python or on Octave or Matlab. You can select also one of the problems that given as exercises in our course, especially for those which has some application. Or in model also, I put some signals that it was collected from some machine, and then I told if you can find some faults in that signals, whatever problem that. But I encourage you to submit something. At least you will get some points. That's. Any questions? Okay. So everyone register his name here. Okay. Thanks a lot. Thank you.